Okay, let's go. Happy Friday, everyone. Welcome back. Homework 3. The first one I talked about how to do last time. You should compute the probability of return in exactly for the first time in exactly n steps and add those up and find the mean. And since I already talked about it, I won't bring it up again, but let me know over the weekend if you're having trouble. In problem 2, it's just the numerical powers of the matrix to kind of investigate the limit. And how would you identify a transient state? A transient state you would eventually escape from, never to return again. So if the state 3, say, were transient, the probability of going from 1 to 3 in an infinite number of steps is going to be 0. And that could be either because you can't go from 1 to 3, or you did, but you can't return to 3 an infinite number of times. So you're looking for a column of zeros if there is transience in there. Okay, 3 is nothing we did in class, so it's just an expectation problem because I want to use this property soon. So you don't have to wait on me to cover a specific topic, but I would write out the expected value. No, I wouldn't. I would write out the right-hand side of that thing you want to show, and then write out a few terms, and then break up each term into a sum of things and collect terms. And I think you'll see it. Okay, 4 I think is maybe the trickiest one, maybe not. It's the most non-standard. So in 4A, we're looking at let me start sharing my screen so I can write a few things. In 4A, we're looking at the expected number of hits on a state J starting from a state I. By the way, I did finally click, every time I share my screen, I have an option to share it with a Roku. It's my neighbor's Roku. I finally did this last night, but I need a code, so I can't just pop up Markov stuff on their TV at will. So we need to pair it each time. I think it would be great if I could. Okay, so in 4, we have talked about starting at state I, the expected number of returns to state I. And remember when I was transient, we computed the expected number of returns to state I. I didn't call it NI there, I just called it N at that time. And we got that this was GI over 1 minus GI, where GI is the probability you will return to state I. And we did that by writing the total number of hits on I as a sum of indicators. And so that's what I would do here for part A. I would say that the number of hits on J at times greater than or equal to 1 is a sum as n goes from 1 to infinity of the indicator that the nth value of the chain is in state J. That's really what we did back in that proof of the expected number of hits on a transient state. And now you just want to take the expected value with respect to I, and it's just, do you understand the notation really? Because the result's going to fall out pretty quickly. Remember, the expected value of an indicator is a probability. So a little more maybe tricky would be that if J is transient, we want to show that the expected number of hits on J starting from I is finite. And one thing that might come to mind when you start this is, can you even get from I to J? And it doesn't matter. So that's what I would condition on. I would say the expected number of hits on J starting from I is the expected number of hits on J given, I need to work out a better notation. We can get from I to J, and that gets multiplied by the probability we can get from I to J. And then the other part of this would be, so I'm conditioning on a single event, which has 2 possibilities. I can get from I to J, or I can't get from I to J. So then I would want the expected number of hits on J given we can't get from I to J. times the probability we can't get from I to j. And the second expectation is 0 because it's saying what is the expected number of hits on state j starting from I? And you're in the case where you can't even get to j at all. So this whole term is 0. And now this, maybe I didn't write this, the English is not completely accurate, but given you can get from I to j, then you start counting the number of hits on j starting from j. And so we don't really have notation for the probability under that yellow circle, but we can use a similar, you don't have to use any notation. You can leave that probability statement there, but I would use something similar to what we've been using with our GIs. Now our GI is the probability starting from I that we will return to I in finite time. And I'm gonna let Gij be the probability starting from I that you will hit j in finite time. And we can write that more formally with one of those hitting times, Tj. But if you do that and go back to what's on the top there, you get the expected value starting from I of nj is going to be this Gij times the expected number of hits on j starting from j. So we're in the case where we hit j as opposed to the other case where we don't get to j from I, and then we just start counting the number of hits on j starting from j. And I think you know an expression for this from part A. And I don't want to talk about C yet. I'll let you stew on that one for a while. But these are the 3 steps, or the 2 steps, and then the conclusion for my favorite way to prove that you can't escape, that any finite state space has to have a recurrent state. I think it's the slickest way to show it. And part C is one of those things that may, I don't know how you're going to feel about it, but it's probably something some of you are going to struggle with, and then you're going to see it, and then it's going to be so darn obvious, I think. But you may struggle for a while, and that's okay. Come to my office hours or email me over the weekend. By the way, if you're a grad student doing number 8, I would try to find pi sub I. And I think you're going to find that pi sub I relates somehow to pi sub I minus 1. And so then you can be recursive, and you could say that pi sub I is some kind of constant in front of pi sub 1. And then how would you find that constant? You need all the pi's to add up to 1. So if you are summing this left side over all the i's and summing this over all i's, this is a constant and will come out. And that coefficient, I think, will not be, that sum is probably not convergent. So this actually would make more sense once I get onto my first examples today, because we got to solve for some pi's. Okay, let's do new stuff. And by new stuff, I mean what we were doing last time. But just a brief recap, the probability of going from I to j in n steps, we've been denoting by this Pij super n, as I call it. And I keep saying super n. I don't want to say to the nth because it's not an nth power, but this is the probability we go from I to j in n steps. And last time we were talking about a limiting distribution. And so this is kind of where the chain goes after a long time. Hopefully it will settle down somewhere. Like you won't have a periodic thing where you just keep flopping back and forth between 2 states or 2 classes. And hopefully it will settle down to some place that's independent of the starting value. And if it does, we define this limit as pi j. And this is the long-term probability of being in state j. And we defined it as the limit as n goes to infinity of Pij super n. And if that limit exists and is independent of I, we saw last time that these numbers will be between 0 and 1 and sum up to 1, and so they form a probability distribution. We also stated a theorem last time that said when this limit exists, and That was one of several pi theorems that we will get to, but I wanted to do some more concrete calculations today, especially to help you with the rest of the homework. So after we talked about the limiting distribution, we talked about the idea of a stationary distribution. And now that I have a little more time and not so rushed, let me try to motivate this better than just throwing the stationary equation up there. So this is a distribution that is maintained through each step of the Markov chain. So what do I mean by that? Suppose you want to find the probability that x1, so we're going to start a chain from time 0, but you want the probability that x1 equals some j. You know how to do this problem. You've seen problems like this. You need a starting value, and so you could condition on where you were at time 0. So I can write this as the sum over all I in the state space of the probability that x1 is j given x0 is I times the probability x0 is I. And that conditional probability there, that's just the p sub ij. So this is little p sub ij probability x0 equals I. And the idea behind a stationary distribution is if you started your chain according to a draw from this distribution. So what the heck does that mean, a draw from this distribution? If my stationary distribution on say 3 states was pi1 is 1/2 and pi2 and pi3 are each 1/4. If you were thinking about simulation, I would start the chain using some kind of algorithm that will spit out the number 1 half the time, the number 2 1/4 of the time, and the number 3 1/4 of the time, and that would be where I would start my chain at time 0. So starting with a draw from this distribution. And so if you want the distribution to maintain, to be stationary over time, to not be changing, then you would like the probability here to be, you would like these probabilities to come from the same distribution. So if there's one pi I, that is going to be the probability that xn is I, then you can put it into this equation up here. And what it's saying is pi j is the sum over I of Pij, so this is just if there's such a thing, pi I. But this is the stationary equation that you want to solve for to see if there is such a distribution that can maintain at each time point. Stationary, not changing in time. Okay, the last thing I'm going to kind of review is because I had a small error, it didn't really affect anything, but at the end of what I was saying last time, and that is that any limiting distribution is stationary. And we were using the Chapman-Kolmogorov equations to prove this. Stationary. So we defined pi I to be the limit as n goes to infinity of the probability starting from anywhere. So I'm going to use a k because I've got the I already and I do want to use a j. This k is arbitrary. The probability to go from k to I in n steps. And so we just want to check that that equation that's circled in some sort of weird bean shape will hold with this definition. So I'm going to start with the right-hand side. I'm going to plug in this definition of pi and go. So, so this is the proof. Define this, and then look at the right-hand side. This is the sum over I of pi I Pij, and this is the sum over I of the limit as n goes to infinity of Pki n, and then that's times Pij, and then I interchange the limit and the sum, so Pki n Pij. And then at this point, here's where my mistake was. That sum is the Chapman-Kolmogorov equation. It's saying we're going from state k all the way to j in n plus 1 steps, and we're kind of conditioned on where we are at n steps. So this is p k j super n plus 1. And last time I put an n there. which technically was okay because in the limit they're the same, but that's not what I meant. So this is equal to this. If I have the n there, or at least they're equal in the limit, but I'm not going to try to claim that's what I meant. Right, so if this probability, we're assuming this probability as n gets large is going off to pi of the second state. And who cares if it's getting large plus 1? This is going to be pi j by definition of our limiting distribution. So if you start with the left side here to the right side, that is the definition of stationarity. We do need to talk about existence and uniqueness and stuff, and but I wanted to do at least some examples because you've got a couple of these to do on the homework. So I put a note in the notes. So a limiting distribution may not exist, but if it does, we've seen that it's stationary. A stationary distribution may not exist, but if a limit exists, then that's not true because it's stationary. The stationary distribution doesn't have to be unique. Going back up to this two-circled thing up here, come on, scroll. There may be more than one kind of probability distribution I can use to describe the distribution at time 0 and time 1 for which this equality is going to hold. So we have a lot of things to talk about in those pi theorems about existence and uniqueness. But for all your computational stuff, like on this homework, really in this class, unless I'm specifically asking you about a kind of bad pathological example, I want to convince you when and where, but please just assume that the limit exists and there is a unique stationary distribution. So there's only one pi we're talking about. It's stationary, it's limiting, and there's no others. Okay, with that said, so it's an example. I will have another example, but I'm not numbering them. Okay, so suppose we just have a state space like 0, 1, and we have a transition matrix that looks like 3/5, 2/5, and 3/4, 1/4. How do we find pi? An example of how I probably asked this question on the homework is find the long run proportion of time this chain spends in state 1. And then you would say, well, that's the limiting distribution, which is the same thing as the stationary distribution. And they are one and the same and everything is unique. So let's solve the stationary equation. Okay, so if you look at the stationary equation, which right after this example, I will rewrite with a matrix and vector. Then if you do this for j equals 0 and realize that you're only summing over two things, you get pi 0 equals pi 0 p 0 0 plus pi 1 p 1 0. And if you do this with j equals 1, you get pi 1 is pi 0 p 0 1 plus pi 1 p 1 1. So that's just me going through this, plugging in j equals 0 and j equals 1, and realizing there's only two i's to sum over. So here's a system of equations to find pi. And in fact, I have specific things here. So in my problem, this is 3/5, for example. But in general, to write out the sum for each equation, you are running the pi for, or say 0 up here, you are running down the 0 column to get the coefficients. Let me write that actually, sorry. Let me copy and paste this. So that didn't make sense because I didn't write the equations specifically. So if I go back to write the equation specifically, what I have is pi 0 is 3/5 pi 0 plus 3/4 pi 1. And then I have pi 1. So for pi 1, I'm going to look at the 1 column and run down the column to get the coefficients for all of the pi's. This is 2/5 pi 0 plus 1/4 pi 1. Run down the columns. So our transition matrix is kind of got some structure to it. The rows add up to 1. And because of this, these equation, the second equation is actually redundant here. So if you take these and try to solve for pi 0 and pi 1 any way you want, like solve for one of them and substitute or make a little nice 2x2 matrix and vector and invert the matrix, you're not going to be able to solve for pi 0 and pi 1. If you try to solve this, you can't just solve it and see what happens. What I'm trying to say is there's an infinite number of pi's that can satisfy this, but not an infinite number of pi's that form a probability distribution. So we need to include the fact that pi 0 plus pi 1 must be 1. That's a constraint here that now makes this solvable. With 2 unknowns, we only need 2 equations. So I definitely want to use this equation because if I use the 2 top ones, I'm not going to get anywhere. So I would pick either one of them, and the sum is 1. So I'm going to take this one and this one. And so you can do this any way you want. Here's a yellow circle representing that I'm working with those equations. You can line those up and subtract a multiple of 1 from the other. You can do back substitution. You can use a vector and matrix. Yeah, so check it out. Make sure you can do it. But in the end, you should get pi 0 is 15 out of 23. And pi 1 is the remaining 8 out of 23. So if going back to the original problem, you got a state space and a transition matrix, and someone says to you, what is the long run proportion of time you spend in state 1? You would say that's a limiting probability, which is also stationary. And we're assuming they are one and the same and unique, so there aren't multiple stationary things. So let's solve the stationary equations by writing down this and writing it out for all the different values of J. So yeah, we were just talking about, Sage and I were just talking about eigenvalues and eigenvectors. So look at the so-called stationary equation. And now I'm going to write out what that is, which is pi j is the sum over I of pi I Pij. What this is pi j is the sum over I of pi I Pij. And what I'm trying to say is the right-hand side is the jth element of the row vector pi times p. I'm going to put a vector here to really emphasize it, but a lot of the times we just write pi and it's vector valued. So if that's the jth element, if this holds for all j, this is going to imply, so this is for all j in the state space, this is going to mean that the pi vector you get from multiplying the pi vector on the left side of the transition matrix. This is just another form of the stationary equation. And so this is what Sage was talking about. We see that this means that pi is a left eigenvector of p with eigenvalue 1. So I'm sure you've seen eigenvectors, but left eigenvectors means you have to multiply the pi on the left. So pi is a left eigenvector of p corresponding to or with eigenvalue 1. If you're not really good with your linear algebra stuff, that's okay. You don't have to make this a matrix vector system. Yeah, we'll show both of these things. So we can show that the largest eigenvector, the largest in magnitude eigenvector of a probability transition matrix P is 1. And this is that eigenvalue. The largest eigenvalue is 1. So all the other left eigenvalues or eigenvalues corresponding to left eigenvectors are going to be in magnitude less than 1. That comes from the fact that it is a stochastic matrix. Just stating this for now because I want to do more examples. And in fact, the rate of convergence of taking the n-step transitions, the rate of convergence to the limit is controlled by the magnitude of the second largest eigenvector. You don't have to get that down now. It's just interesting. Eventually we'll talk about it and I'll write it all down. So most of our systems are going to be pretty small. So if you're uncomfortable with this stuff, you can like back substitute your way through. And on something like an exam, I wouldn't make you do this. I would say set up the system of equations and indicate what you want to solve for. Like, I want to know pi 0. All right, so I have another example, but I first wanted to say a couple more things about the stationary equation. So stationarity holds, let me write this, it's kind of like a quote from me. Stationarity holds at all fixed time points. So we can show this by induction, but before we do, let's just think about it kind of with a picture. If there is some distribution of our values at time 0 that is stationary, if we started with a value drawn from that distribution, meaning if those are states 1, 2, and 3, we started with state 2 more often than the others. If it's stationary, then the result at time 1 is also going to be a draw from that distribution. So these two histograms represent, I picked a starting value and I went forward and I got an ending value. I picked a whole bunch of starting values and made a histogram. And then I made a histogram of all the ending values, and those have the same shape. That's what it means for the distribution to be stationary and not changing in time. So clearly, if you went forward another time step, you would get the same shape because you can just relabel time step 1 as 0. So the end of that yellow path is the beginning of a new path being drawn from that stationary distribution. So you'll go somewhere else. You can't see stationarity based on one point. But if you were to repeatedly do this over and over again and just collect the values at each time step and make a histogram at each time step, you'll see the same shape. So what this means in terms of an equation is that pi j is the sum over I of pi I Pij super n. It's another version of the stationary equation. I can put n-step transitions in there. I did say fixed time points because we're going to see a problem if n is random. But we can prove this thing in the box using induction on n. So prove by induction on n. So my first step would be to prove it when n equals 1, and that's our definition of stationarity, because the assumption here is I have a stationary distribution, so it satisfies pi j is that sum, and I want to show that it holds for other n. So one, step 1 of my induction, n equals 1 is satisfied because I'm starting with a stationary distribution and saying that then it stays stationary at all fixed time points. So this is because we're assuming pi is a stationary distribution, and the very definition of that is what's in my yellow box, but with n equals 1. Then I'm going to assume that it holds for n equals k. And I'm just not going to bother to write that, but I would right now write the thing in the yellow box, but I would put k in for that exponent. And then finally, we want to show that it holds for n equals k plus 1. So let's do it. I'm going to start with the right-hand side, which is the sum over I of pi I p I j super n plus 1. And then I'm going to split up that traversing from I to j and n plus 1 steps into the first n steps and then the last step. And then I'll just sum over all the places I could land after n steps. So this is the sum over I of pi I, and then the sum over all like k in the state space of PIK in n steps, and then PKI in 1 step. Not that you have to write that one. Chapman-Kolmogorov right there. And then if you interchange, you continue to do this math that makes some of you cringe, I'm sure. Interchange the order here, then the inner sum becomes pi I PIK super n, and then you've got a PKI. And then by the induction step 2, we know that thing in the square brackets is pi sub k, sum over k of pi sub k PKI. And then by the induction step 1, the fact that pi is stationary, this is going to be, something went wrong. Oh, I moved to, yeah. So this I was going from I to j, and then I wrote it as going from I to k in n steps, and then k to I. This second subscript way up here in the right corner should be a j. J. And then this guy should be a j.
Don't you mean the ones that are rid of it?
Yes, I do. No. Yes, 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 I do. This guy is a j. And this guy is a j. Okay, so by the stationary equation, this is going to equal pi sub j. I wanted. Yeah. It's a group effort, but we did it. We showed that if you take n plus 1 time steps and run them through the stationary equation, you do get back down to the pi sub j. Because originally this said the sum of the pi i's, pij, is equal to pi sub j, and now we showed that it still holds with this exponent in here. Question? Okay. I did say all stationary holds at all fixed time points. So stationarity, this is just a note that will become important later when we do a little bit more when we do some simulation stuff. So stationarity may not hold at random time points. It depends on how they're related to the process. If they're independent of the process, we actually can see that the stationary. So if I am going, hold on, let me write this down, at random time points, i.e. pi j is not necessarily, although it could be in some cases, the sum over I of pi I, pij, and then moving a random number of points and a random variable. So, yeah. Yeah. So a question in the chat, I was supposed to show that this holds for n equals k plus 1. Instead, I was just showing it holds for n plus 1. So all the n's in here should be k's. Assuming that you want to show what I stated. You can also do induction without introducing the k's. But yeah, sorry about that. So let me convince you of this claim by an example. So if we consider the state space we had and the transition matrix we had, where we found a stationary distribution, was the 3/5, 2/5 one, I think 3/5, yeah. 3/5, 2/5, 3/4, 1/4. We found a stationary distribution that was non-trivial. It's like 13 over 25 and 8/25, I think. So if I let n be the first time the chain hits 0, so this is not a greatest example. It would have been better with more states, but I start it no matter how I start it. So this is 0 and this is 1. Let's say I start at 1, or I start with a draw from the stationary distribution, in which case my hitting time is going to be 0. But suppose I move along, and then I hit 0, and that's n, my random variable. The sum over all I of pi I, Pij, super n, this is going to be the probability. This is supposed to be the probability we're in state J, but the probability we're in state 0 was 13/25, and the probability we were in state 1 is 8/25, and the probability we go from, am I saying this wrong? So if you start stationary back here, there's some distribution, right? And you're not going to see that distribution at this time point. You're just going to see a whole histogram rectangle with, this has height 1. The only draw you will get at that time, that random n, is 0. So you won't be getting 0 13/25 of the time. You're going to be getting it 100% of the time. So clearly stationarity is not holding. I need to be more specific and say, let n be the first time after time 0 where we hit 0. Then I need to start my simulation from state 0, 13/25 of the time, and state 1, 8/25 of the time, and run forward until the first time I hit 0 at times greater than or equal to 1. The distribution at that time is not this. It is now completely, it's 1. Sorry, the distribution gives weight 1 to state 0, not the 13/25 and the 8/25. All right, yep, I had those numbers wrong. Those even add up? No. It was 23rd. Yeah, well, those add up, but these are not right. Thank you. It was 15/23 and 8/23, but the point still holds. Okay, I have one more example that I think we can get to today, and that is the barefoot runner example. So, last example, which I don't even think we'll finish. You have a runner, person that's running, they live in a house. There are 2 doors to the house, say the front door and the back door. The runner has 6 pairs of running shoes. And I'm gonna forego some of the English. I will type it up. Let's just draw this with a kind of a picture. So this is the runner's house, and there's a door, and there's a door. The runner has 6 pairs of shoes that he or she leaves in piles by the door, much like me. So maybe on one day, each of these circles is representing a pair, not a single shoe. So that's 2 pairs of shoes and maybe 4 pairs of shoes. They pile them up by the door. And each day, the runner randomly selects a door. If there are shoes there, the runner puts on the shoes and goes for a run. If there are no shoes there, the runner runs barefoot. Yeah, that's correct in the chat. And then the runner comes back, and if the runner was wearing shoes and is not barefoot, well, the runner comes back and randomly selects a door. And if the runner was wearing shoes, they drop them at that door. So I know this is not going to make that much sense unless I write all those details out. But I'm going to let xn be the number of shoes at the departure door. So please check out the notes for more detail and maybe the beginning of next lecture on the nth day. So I want, what is the long run probability that this runner runs barefoot? The long run proportion of time or probability. The runner runs barefoot. So this means if xn is the number of shoes at the departure door, i.e., we want to find the long run probability of being at state 0, which is equivalent to the stationary probability at state 0. Remember, we're assuming everything exists and is unique. I'm out of time. See if you can't fill out this transition matrix. It's a little tricky. And then we're going to see that it's a special transition matrix. It's doubly stochastic. The columns also sum to 1. And when that happens, there's an easier way to find the stationary distribution than to start making all those equations. Next time on Markov chains. Have a good weekend.